Now we're ready to begin talking about actual program optimizations, and we'll begin with local optimizations. Local optimization is the simplest form of program optimization because it focuses on optimizing just a single basic block, so just one basic block. And in particular, there's no need to worry about complicated control flow. We're not going to be looking at the entire method or procedure body. Let's dive right in and take a look at a couple of simple local optimizations. If x is an integer valued variable, and from here on we'll assume that x has type int. So let me just write that down. We're going to assume that x has type int in all of our examples on this slide. Then the statement x equals x plus 0, well, that doesn't change the value of x. 0 is the additive identity for plus. We're just going to assign x the value it currently has, and so this statement is actually useless. It can just be deleted from the program. Similarly, for x equals x times 1, multiplying by 1 will not change the value of x, and so that statement can also be removed. And in this case, these are great optimizations because we actually save an entire instruction. Now, some statements can't be deleted, but they can be simplified. A simple example of that is if we have x equals x times 0, so that can be replaced by the assignment x equals 0. And again, we still have a statement here. We still have to execute a statement, but this statement may execute more quickly because it doesn't involve actually running the times operator. It doesn't involve referencing the value of x. Presumably x is a register. That doesn't really cost anything. But it's possible that this instruction over here will execute faster than this instruction over here. Now, on many machines, that's not the case. In fact, this assignment on the right will take the same amount of time as the multiplication on the left. But as we will see, having an assignment of a constant to a variable will actually enable other optimizations. So this is still a very worthwhile transformation to do. An example that's almost certainly an optimization is replacing the exponentiation operator, raising a value to the power of 2 by an explicit multiply. So here we're computing y squared, and over here we just replace that by y times y. Why is this a good idea? Well, this exponentiation operator here is almost certainly not a built-in machine instruction. Probably that's going to wind up in our generated code being a call to some built-in math library, and that will involve a function call overhead, and then there'll be some kind of general loop in there to do the right number of multiplies, depending on what the exponent is. So in the special case where we know that the exponent is 2, it's much, much more efficient to just replace that call to exponentiation by an explicit multiply. Another example of substituting one kind of operation for another in a special situation is if we have a multiplication by a power of 2, we can replace that by a left bit shift. So here we're multiplying by 8. That's the same as shifting the binary representation of x over by 3 bits. And that will, in fact, compute the same thing. And it doesn't even have to be a power of 2. If we have a multiplication by some other number that's not a power of 2, that can be replaced by some combination of shifting and subtractions. Okay, so we can replace the multiply by some combination of shifts and arithmetic operations, simpler arithmetic operations. Now, these last two here, I should point out, these are interesting transformations. On modern machines, generally this will not result in any kind of speed up because on modern machines the integer multiply operation is just as fast as any other single instruction. On historical machines, these were actually significant optimizations. So all of these instructions together are examples of algebraic simplifications. So that just means exploiting properties of the mathematical operators to replace more complex instructions or more complex operations by simpler ones. One of the most important and useful local optimizations is to compute the results of operations at compile time rather than at runtime if the arguments are known at compile time. So for example, let's say we have a 3-address instruction, x equals y op z, and it happens that y and z are both constants. These are both immediate values. These are literals in the instruction. Then we can actually compute the result of the right-hand side at compile time and replace this by an assignment to a constant. So for example, if we have the instruction x equals 2 plus 2, that can be replaced by the assignment x equals 4. And another example, which is a very common and important one, is if the predicate of a conditional consists only of immediate values, then we can pre-compute the result of that conditional and decide what the target of the conditional will be, what the next instruction will be at compile time. So in this case, we have a predicate which is going to be false because 2 is not less than 0, and so we will not take the jump, and so this instruction can just be deleted from the program. If we had the other case, if 2 was greater than 0, so this was some predicate that was guaranteed to evaluate true, then we would replace this conditional by the jump. Okay, this would become an unconditional jump. Right? And this class of optimizations is called constant folding. Right? And as I said, this is one of the most common and most important optimizations that compilers perform. Now, there is one situation that you should be aware of in which constant folding can be very dangerous. And this situation is actually very instructive as well. And so while it isn't that common, I want to mention it because it's something that really illustrates some of the subtleties of program optimization and programming language semantics. So what is this dangerous situation? So let's consider the scenario where we have two machines. We have a machine X and we have a machine Y. Okay, and now the compiler is being run on machine X. And the compiler is producing code, the generated code. This is the generated code produced. This is the output of the compiler over here. That's going to be run on machine Y. So this is a cross compiler. Okay, so you are running the compiler on one machine, but you're generating code for a different machine. And why would you want to do that? Well, the common situation in which you want to do this is that this machine Y over here is a very weak machine, so weak in the sense that it's very slow, has very limited memory, maybe very limited power, that it's beneficial to develop your program and even compile it on a much more powerful machine. So many embedded systems codes are developed in exactly this way. The code is developed on some powerful workstation, but you're actually compiling it for some small embedded device that will actually execute the code. Now, the problem comes if X and Y are different. So consider the situation where X and Y are different machines, different architectures. All right, and I've been implying that they are, but they don't have to be. I mean, you could compile on one kind of architecture and run the same code on the same architecture. But the interesting situation is when X and Y are different architectures. And so let's consider something like in machine X, let's say we have the instruction A equals 1.5 plus 3.7. Okay, and you would like to constant fold that down to A equals 5.2. All right. Now, the problem is that if you simply execute this as a floating point operation on architecture X, the round off and the floating point semantics on architecture X may be slightly different from the semantics on architecture Y. It could be that if you did it in architecture Y directly, that you might get something like A equals 5.19. There might be a small difference in the floating point result, depending on whether you execute the instruction here or here. And this becomes significant in the case of constant folding and cross-compilation because some algorithms really depend on the floating point numbers being treated very, very consistently. So if you're going to round off in the operation in one way, you need to do it that way for every time you do that particular operation. And by shifting the computation from runtime, when it would have executed in architecture Y, back into the compiler, when it ends up executing in architecture X, you can change the result of the program. So how do cross-compilers actually deal with this? So compilers that want to be careful about this kind of thing, what they will do is they will represent the floating point numbers as strings inside the compiler, and they will do the obvious long-form addition and multiplication, division operations, all the floating point operations directly on the strings, keep the full precision inside the compiler, and then in the generated code produce the literal that is the full precision floating point number, and then let the architecture Y decide how it wants to round that off. Okay, so that's the really careful way to do constant folding on floating point numbers if you're worried about cross-compilation. Continuing on with local optimizations, another important one is to eliminate unreachable basic blocks. So what's an unreachable basic block? That is one that is not the target of any jump or fall through. So if I have a piece of code that can never execute, and it might never execute because there's no jump that jumps to the beginning of that piece of code, and it doesn't follow after another instruction that can fall through to it, well, then that piece of code, that basic block, is just not going to be used. It's unreachable, and it can be deleted from the program. This has the advantage of making the code smaller. So obviously, since the basic block is unreachable, it's not contributing to the execution cost of the program in terms of the instruction count. So the code is never executed, so it's not really slowing down the code because extra instructions are being executed. But making the program smaller can actually make it run faster because of cache effects. So the instructions have to fit into memory just like the data. And if you make the program smaller, it makes it easier to fit the program in memory, and you may increase the spatial locality of the program. Instructions that are used together may now be closer to each other, and that can make the program run more quickly. Before continuing on, I want to say a word or two about why unreachable basic blocks occur. So why would a programmer in their right mind ever write a program that had code in it that wasn't going to be executed? And there's several actually ways in which unreachable code can arise, and it's actually quite common. So this is an important optimization. Getting rid of the unreachable code is actually fairly important. Perhaps the most common situation is that the code is actually parameterized with code that is only compiled and used in certain situations. So for example, in C, it would be sort of typical to see some code that looks like this. If debug, then execute something, where debug is a pound-defined constant. So in C, you can define names for literals. So you say something like this. You might define debug to be 0. And so you might see a program that had this piece of code in it. And what this literally means is that this piece of code is equivalent to if 0, then blah, blah, blah. All right, so when you're compiling without debugging, you have debug defined to 0. When you're compiling with debugging, you would change this line to define debug to be some non-zero constant. So in this case, when you're compiling without debugging, what will happen? Well, we'll see that this predicate is guaranteed to be 0. Constant folding will take care of that, and that will result in an unreachable basic block on the then branch, and then that code can be deleted. And so essentially the compiler is able to go through using the optimizer and strip out all of the debugging code that isn't going to be used since you're compiling without debugging. Another case where unreachable code comes up is with libraries. So very frequently programs are written to use generic libraries, but the program might only use a very small part of the interface. So the library might supply 100 methods to cover all the situations that various programmers are interested in, but for your program you might only be using 3 of those methods. And the rest of those methods could potentially be removed from the final binary to make the code smaller. And finally, another way that unreachable basic blocks occur is as the result of other optimizations. So as we will see, optimizations frequently lead to more optimizations, and it could be that just through other rearrangements of the code that the compiler makes some basic block redundant and able to be deleted. Now, some optimizations are simpler to express if each register occurs only once on the left-hand side of an assignment. So that means if each register is assigned at most once, then some of these optimizations are easier to talk about. So we're going to rewrite our intermediate code always so that it's in single assignment form. So this is called single assignment form. And all that means is that if we see a register being reused, like over here, we have 2 assignments to the register X. Okay, we're just going to introduce another register name for one of those assignments. So in this case, I'm just going to rename the first use of X here, a definition of X here, to be some new register B. I'll replace the uses of that X by the name B, and now I have an equivalent piece of code that satisfies single assignment form. every register is assigned at most once. Let's take a look at an optimization that depends on single assignment form. So we're going to assume that basic blocks are in single assignment form, and if they are, then we're going to know that a definition of a register is the first use of that register in the block. And so in particular, we're also ruling out things like this. So there could be something like this where X is read, and then later on X is used. Okay, sorry, X is read, and then later on X is defined. So we're not going to allow this. This register here would have to be renamed to something else, say Y, and then the uses of X later on here renamed to Y. All right, so we're going to insist that whenever we have a definition of a register in a basic block, that is the first use of that register in the block. All right, and if that's true, if we put things in that form, and that's easy to do as we've seen, then when two assignments have the same right-hand side, they're guaranteed to compute the same value. So take a look here. This example. So let's say we have an assignment X equals Y plus Z, and then later on we have another assignment W equals Y plus Z. And we said that there can only be one assignment to X in any basic block. So all of these instructions that are elided here, they can't be assigning to X. And they also can't be assigning to Y and Z. Y and Z already have their definitions, so Y and Z can't be changed. And that means that X and W here actually compute the same value. And so we can replace the second computation, Y plus Z, by just the name that we already have for it, X. Okay, and this saves us having to recompute values. All right, so this is called common subexpression elimination. Common, this is a rather long name, subexpression elimination. And this is another one of the more important compiler optimizations. This is actually something that comes up surprisingly often and saves quite a bit of work if you perform this optimization. So another use of single assignment form is that if we see the assignment W equals X in a block, so here the register W is being just copied from the register X, then all subsequent uses of W can be replaced by uses of X. So for example, here we have an assignment to B, and then we have a copy, A is equal to B, and then down here we have a use of A in the last instruction. Well, that use of A in the last instruction can be replaced by a use of B. And this is called copy propagation. Okay? We are propagating copies through the code. And by itself, notice that this makes absolutely no improvement in the code. It's really only useful in conjunction with some of the other optimizations. So for example, in this case, after we do the copy propagation, it might be the case that this instruction can be deleted. If A is not used anyplace else in the code, then this instruction can be removed. Now let's do a little more complex example and use some of the optimizations that we've discussed so far on a slightly bigger piece of code. So we're starting with this piece of code here on the left, and we're going to wind up with this piece of code on the right. And how does that work? Well, first we have a copy propagation. So we have A is assigned the value 5, and so we can propagate that forward and replace the use of A later on by 5. And I should say that when the value that's being propagated is a constant rather than a registered name, it's called constant propagation instead of copy propagation, but it's exactly the same thing. We have a single value assigned on the right-hand side, either a register name or a constant, and we're replacing uses of that in later instructions by that register name or constant. Okay, so once we have replaced A here by 5, now we can do constant folding. Now we have two constant arguments for this instruction, so this 2 times 5 can be replaced by the constant 10. Now notice we have another assignment of a constant to a register, and so we can propagate that constant forward. We can replace the subsequent uses of X by the number 10, and now we have more opportunities for constant folding. 10 plus 6 can be replaced by the value 16. All right, now we have another value here, which is a constant assignment. Sorry, another instruction here, which is just an assignment of a constant to a register. So we can propagate that constant forward. All right, and we wind up down here with 10 times 16. And I see over here in my final example here, I didn't bother to propagate the 10 to X, but we could do that. And so we can either do this optimization, so x times 16 if we didn't do the propagation would be equivalent to x left shifted 4, or we can just replace this by 10 times 16, that would be even better, and we wind up with t being assigned the value 160. Returning to an idea I mentioned a couple of slides ago, let's say there's an assignment in a basic block. Some register W is assigned some value that's computed on the right-hand side. But let's say that W, the register name, is not used anywhere else in the program. It doesn't appear anywhere, not only in this basic block, but in any other part of the procedure in which this statement appears. Well, then the statement is dead and can be just deleted from the program. And dead here means it does not contribute to the program's result. Since the value that we write into W is never referenced anywhere, W is never used, doing the computation of W in the first place was a waste of time, and so we can just delete that computation. Here's a simple example. Let's assume that the register A is not used anyplace else in the program. And the first thing we have to do, so here's our initial piece of code. The first thing we do is we put it in single assignment form. And so I've renamed here this register X to be a register B. Okay. And once we do that, let me do that. So we say B equals Z plus Y and A equals B. And then we propagate this copy forward. All right. So we've now replaced this use of A by B. So this takes us to this state where we have this piece of code. Now we can see that we have an assignment to A. A is not used in the subsequent instruction. We already said that A is not used any place outside of the basic block. And so the assignment A equals B can be deleted, and we wind up with this shorter basic block. Now, each local optimization actually does very little by itself. And some of these optimizations, some of these transformations that I presented actually don't make the program run faster at all. They don't make it run slower either, but by themselves, they don't actually make any improvement to the program. But typically, the optimizations will interact. So performing one optimization will enable another. And we saw this in the little example that I did a few slides ago. So the way to think about an optimizing compiler is that it has a big bag of tricks. It has a lot of individual program transformations that it knows. And what it is going to do when faced with a program to optimize is going to rummage around in its bag looking for an optimization that applies to some part of the code. If it finds one, it will do the optimization, it'll do the transformation, and then it will repeat. It'll go back and look at the program again and see if there's another optimization that applies. Then it will just keep doing this until it reaches a point where none of the optimizations it knows about can be applied to the program. Next, we'll take a look at a bigger example and try applying some of the optimizations that we've discussed to it and see how far we get. And of course, this example has been constructed to illustrate many of the optimizations that we discussed. So, first thing we can do, there's a couple of opportunities for algebraic simplifications. So we can replace the squaring up here by a multiply, and down here we had a multiply by 2, which we can replace by a left shift of 1. Next, we can observe that we have some copies and constants. So we have a constant assignment to B and a copy assignment to C, and those can be propagated forward to the uses of B and C. Once we've done that, we can do constant folding. So here in the assignment to E, the arguments to the shift are all constants, and so that can be replaced by an assignment that E gets the value 6. Next, we could observe that we have a common subexpression that we can eliminate, that both A and D have the value x times x. So the assignment to D can be replaced by a copy, that D now gets the value of A. Now we have two opportunities again for copy and constant propagation. The assignment to D and the assignment to E can be propagated forward. And finally, we can do a bunch of dead code eliminations. So assuming that none of these values, B, C, D, or E, is used anyplace else in the program, all 4 of these statements can be deleted. And this is where we actually get some real performance improvement. So here we actually saving entire instructions, and that's the best kind of savings that we can have. And so we wind up with this as our final form. So notice that A is assigned the value x times x, F is then assigned the value a plus a, and then G is assigned the value 6 times F. Now this is not quite as fast as it could be. All right, there's actually one more algebraic optimization that could be done. We could notice here that F is actually equal to 2 times A, and then we could do some rearrangement here to discover that G is equal to 12 times F, or sorry, 12 times A. All right, and then this statement assignment to F might become dead code, and we could delete it from the program. I think some compilers would actually find this, but I believe that even current state-of-the-art compilers, many of them would not discover this last rearrangement to the program.